Good morning, everyone. Thank you for joining the 6th Microchip Shields Up webinar. Today, we're going to talk about the importance of implementing quantum resistance for critical security functions. My name is Krishna Kumar, KK in short. I'm a product line marketer for the FPGA business unit at Microchip, and I drive Microchip's initiative towards developing a RISC-V ecosystem, what we call the Mi-5 ecosystem. We have with us Louis Sparks, who is the founder, president, and CEO of Veridify Security, formerly known as Secure RF. Quick housekeeping announcement. At any point, if you have any questions, you should be able to find a chat box at the top right corner. You can go there and type in your questions. We will take a look at your questions and answer them at the end of the session. This session is being recorded, and we will have links to the recording posted on our website. In today's webinar, I will give a quick introduction to the latest announcement from Microchip's FPGA business unit, the PolarFire SoC FPGA. And then I'll hand over to Louis to talk about implementing quantum resistance in critical security functions. Okay, so PolarFire SoC FPGA, it's based on our existing award-winning PolarFire FPGA architecture, to which we've added 5 64-bit hardened RISC-V CPUs. The microprocessor subsystem consists of 1 monitor core and 4 Linux-capable processor cores. It also consists of a coherent switch that maintains cache coherence across all cores, a large L2 memory subsystem that can be configured to enable deterministic execution of bare metal and RTOS alongside a rich operating system like Linux. The monitor core can act as a boot core and can monitor runtime system functions. It can also be made to act as a trusted execution environment in your system. The 4 other cores can run a rich operating system like Linux, bare metal, or RTOS in SMP or AMP, symmetric multiprocessing or asymmetric multiprocessing modes. The processor subsystem is connected to the FPGA fabric through a coherent switch and an AMBA bus interface that supports memory protection and quality of service. We also have an integrated DDR4, LPDDR4 controller and PHY, and a slew of hardened peripheral IPs that connect to the processor subsystem and the FPGA fabric. This is a true innovation platform wherein you can get deterministic real-time execution alongside rich operating system like Linux. Thereby, it provides the simplicity of using a Linux-capable system while also doing real-time system control. It is built over our existing strengths in designing really low-power FPGAs and SoCs, so it would be ideal for thermal and power-constrained applications. With secure boot capabilities and a variety of security functions that I'll talk about shortly, PolarFire SoC will enable secure, connected IoT applications. We also bring in our strengths in building reliable FPGAs and SoCs, so PolarFire SoC would suit perfectly for mixed criticality systems. I'd like to emphasize on our low power leadership. Here you can see a benchmark that we did of PolarFire SoC to some of the popular SoC FPGAs out there. The chart here shows CoreMarks per watt performance of PolarFire SoC, the green line that you see here, vis-a-vis competition, the blue, black, and red lines over here. You can see that PolarFire SoC delivers up to 50% lower power compared to other Cortex A9 and A53 based SoC FPGAs. You would also notice that PolarFire SoC would boot and deliver 6500 CoreMarks before any of the competing FPGAs start delivering any CoreMarks. So PolarFire SoC would be ideally suited for low power, really low power applications. Another aspect I'd like to emphasize is our security leadership. PolarFire SoC inherits features from the PolarFire FPGA in terms of security. So it has features such as DPA resistant bitstream programming, anti-tamper. So we have capabilities to monitor voltage, frequency, and temperature monitoring, apart from implementing an active mesh to check for tampers in your system. We have a physically unclonable function, or PUF, that makes each chip unique and the internal keys unique as well. And these keys are known only to the physical actual device. It also has true random number generator and side channel resistant, or DPA safe crypto coprocessor. The crypto coprocessor is available in some of our devices which will have a special marking. So you can offload all your crypto functions to this coprocessor and actually not really worry about these crypto functions affecting your system bandwidth, your processor bandwidth. We will also have a cryptographically bound supply chain assurance. So basically, we have digital certificates injected at the wafer level, and they are verified during every step of our supply chain, from fab to assembly to packaging and test, before it reaches our customers. So the entire supply chain is cryptographically controlled. So these, what I've said so far, are the features of the PolarFire FPGA that are inherited by the PolarFire SoC. Furthermore, PolarFire SoC adds secure boot and options for user-defined secure boot. So if customers are interested in designing their own secure boot, that can be done as well. The microarchitecture is a 5-stage in-order pipeline. So it is inherently Spectre and meltdown immune. It will also have the RISC-V ISA specified physical memory protection to implement trust. And we'll also have SecDead or error correction on all our MSS memories. So PolarFire SoC would be ideally suited to implement secure, connected, reliable, and low power systems. So with that, I'd like to hand over to Louis, the CEO of Veridify Security, to take us through their quantum resistant solution. Louis?
Great, thank you, KK. And thank you everyone who's joining us today. Just before we start, I want to take a moment to point out to those of you on the call that you may have known us as SecureRF, but in recognition of our expanding product and market footprint, we recently changed our name to Veridify Security. And we'll be continuing to deliver our ISO certified and award-winning solutions as Veridify. Next slide, please. For those of you who are not familiar with our company under our old or new name, let me take a moment to introduce our solutions. We are focused on providing authentication and data protection for the smallest processors found at the edge of the IoT. Our quantum-resistant methods include Diffie-Hellman-like digital signature algorithms and hybrid key agreement protocols. We've recently introduced a zero-touch onboarding and secure ownership management solution for IoT devices that I will be talking about a bit more in this webinar. Our methods can be used to solve a wide range of security needs, including user-defined secure boot, as mentioned earlier by KK on the PolarFire SoC, and over-the-air software updates. And we have a range of free toolkits and SDKs for Microchip's PolarFire SoC, and we'll provide a link to get them at the end of this webinar. If any of you have tried to secure a low-resource IoT processor, then you likely have found it a challenge. And why is IoT security so hard? One of the main reasons is that the legacy methods that you're likely using are 35 to 45 years old and really never contemplated a small, low-resource device performing critical functions. As you know, many of the devices at the edge of the IoT that could be talking to a PolarFire SoC rely on a small 32-bit, 16, or even an 8-bit processor, and legacy security simply does not fit. Edge IoT devices today, like a BLE sensor, are often engineered for low energy consumption. So computationally intensive and slow-running crypto creates another hurdle. In some cases, you may be able to turn to symmetric methods like AES for small deployments. But if you're looking to address a large number of devices, tens or hundreds of thousands of units, you will find that symmetric methods simply do not scale. And with today's topic, all of these challenges, you will still need to address the threat of a quantum computer-based attack. So what do we mean when we say quantum resistant or quantum computer-based attacks? People are typically referring to two algorithms or attacks: Grover's search algorithm, which reduces the security level of all methods, public key or private key. That is, a method at 128-bit security level is rendered only 64 bits of protection. So users have to double the security being used. That is, you need to use a 256-bit key to achieve 128-bit security. This provides an additional challenge now for you, since securing all IoT devices typically use methods that run in quadratic time. That is, they need to multiply and divide large numbers that grow in size with the increase in security levels, straining an already struggling processor. Veridify's methods also need to have their key sizes increased, but our methods only grow linearly in time, putting less workload on a small IoT device. The second attack, Shor's, is arguably more concerning, as it breaks ECC and RSA by its ability to factor large primes and solve the discrete log problem. For Shor's attack to work, the method must be based on finite math, be cyclical, and commutative. Veridify's methods are based on infinite theory, are not cyclic, and not commutative, making them immune to this attack, and hence quantum resistant today. Veridify's group theoretic methods are based on a 100-year-old hard problem, and GTC has been studied since the mid-70s, roughly the same length of time as RSA and Diffie-Hellman. GTC uses small operands, 8 to 32-bit numbers, enabling them to easily run on small IoT processors, even as software. GTC methods are small, often needing less than 5K of ROM, are many times faster than ECC and ECDSA, and as a result, consume less energy. Our methods leverage structured groups, sparse matrices and permutations, and arithmetic over finite fields. For those of you interested in learning more, white papers on the math and theories behind our methods are available on our website at veridify.com. For the balance of today's webinar, I'd like to provide a brief overview of the two areas of IoT security that we specifically address. That is, protecting device-to-device, or when two or more processors are communicating on the IoT, and it is critical to make the solution secure. Our tools provide identification and authentication protocols to protect the IoT devices at the edge and protect the commands and the data that is there. And in order to securely deploy and manage a processor in the field, we have recently introduced DOME, our Device Ownership Management and Enrollment solution. DOME is a zero-touch platform that uses a blockchain architecture for each processor to deliver some very unique industry features. Our tools for the PolarFire SoC provide authentication functions to ensure it connects and talks to only trusted devices. The unique session keys generated each time can be used to encrypt and protect data on the PolarFire and the data transmitted to external devices. You want to make sure the firmware instructions on your PolarFire SoC are not compromised, and our methods can be configured to provide both secure software updates and a user-defined secure boot function. DOME is our ownership management solution that fills a unique operational gap in the IoT. It provides a zero-touch onboarding solution to make deploying your devices easier and faster. And it goes beyond typical device management solutions by providing in-field ownership management with ownership transfer capabilities. An IoT device using Dome can support mutual authentication and key or firmware updates in the field. And Dome devices do not require a pervasive cloud or network connection. They only need to connect to their owners. I want to take a moment to distinguish our ownership management model with almost all other IoT solutions that are focused on just device management. Device management does typically recognize that a processor may be in the field for years, even decades, and may have more than one owner. Many devices are small and will never connect to a cloud or network, and that many devices and management systems may rely on a cloud or network to work. And in order to deliver basic security functions, many current systems need large processors or computing platforms to execute their device code. And the methods are designed for a specific or proprietary processing architecture, further limiting your use. And finally, most systems rely on legacy security methods that are not quantum resistant, limiting the length of time and their useful life in the field. Here's a schematic overview that shows how powerful and yet simple and easy it is to use Dome. You can see a PolarFire SoC in the lower left being credentialed and onboarded into the system. The Dome device code requires less than 8K of ROM, and a manufacturer who sells the processor to a distributor simply can ask the distributor for their public credential. They sign it into a block and return the updated credential to the distributor. When the PolarFire SoC ships and is turned on at the distributor's location, it challenges the distributor to prove it is its new owner. The distributor presents its chained credential, and if correct, the SoC recognizes the distributor as its new owner and turns over control and access. This process can be repeated any number of times, and transferring ownership does not require the owner to actually turn on or install the device. As you can see, a dealer, the third owner on the slide, may only take delivery of a unit. Perhaps it's a distributor who only puts it in inventory and then sells and installs it at an end user, who, again, when asked to provide a correct chained credential, can take control and manage the PolarFire SoC at the end. In this diagram, we show a bit more detail. You can see how the ownership credential is maintained in a chain of blocks or blockchain for each processor. The processor only needs to connect with its owner, and the blockchain maintains a lifelong pedigree for each processor in the system. In summary, Dome is a software solution requiring only 8K of ROM on a PolarFire SoC, and it can easily support other 8, 16, and 32-bit architectures. It provides unique in-field ownership management and transfer functions, and Dome-enabled devices can deliver one-way or mutual authentication, supporting key management and firmware updates in the field. A Dome device does not require a cloud connection. Only the owners need to connect to transfer credentials. And all of our appliances and apps are built with Veridify's GTC, making them quantum resistant to all known attacks. I hope you have found our security overview informative, and I thank you for joining, and I thank our co-host, Microchip and KK. Thank you, KK.
Thank you, Louis. So before we end, I'd like to give a quick update on the early access program. PolarFire SoC product family was recently announced last week at the RISC-V Summit. So the PolarFire SoC family ranges from 23K to 460K logic element devices, and we will be sampling in the third quarter of 2020. We have a few soft solutions available for you to get started right away. If you're interested in Checking and in applying for the early access program, you can write to PolarFire SoC at microchip.com, and we can take that discussion forward and see if you can qualify for this early access program. For more information on DOME and Veridify, you can go to www.veridify.com/DOME. To request a free SDK for PolarFire SoC, you can write to info@veridify.com. For more information on PolarFire SoC, you can visit our website, www.microsemi.com/PolarFire SoC. And of course, you can write to PolarFire SoC at microchip.com, and we'll get you more information. If you want to go through our other Shields Up webinars in the past and want to register for the upcoming webinars, you can just Google Microchip Shields Up, and you should quickly get to where you need to be.